Hi guys, welcome again. Let's do this problem. I think it's a really brief, small problem that has to do with normal stress, as you can see here. Okay, so they are asking us. Here you have the whole deal. Okay, now if you ask me why I don't put this in the right way, that's because some students of mine they just send me the pictures and that's what I used. Okay, so this should come from a book that I don't know what's the source. So in that case, I'm sorry to maybe I don't have that information. Okay, so the basic idea here is that you have a rope that it's trying to try to lift this weight, and this weight in this case is 300 pounds. Okay, so 300 pounds, and it's been done, and this is being done by cables. So they talk about these four cables. When I was first looking at this, I really don't know what they mean, but here I think, if I'm right, this is the one, two, three, and you cannot see the other one in the back. That is the four cable. Okay, so each one of these cables, it has a diameter, and they ask us to find the stress that they are subject in this problem, and also to compare it with the ultimate stress. And this comparison is being done with an indicator, and this indicator is called the safety factor. Okay, so this safety factor is something that we use a lot in mechanics of material, in structural design, in aerospace design, and that type of thing, because we want to know how far we are from the ultimate stress in our problem. And if we are really far away, so we do it. We have done it. Okay, so let's just try to see how this thing works. So we have this 300 going up. Okay, and if I just look at the profile, okay, so the profile, so I have these cables. So this is the rope, okay, and it's trying to pull up 300 pounds. And this is a cable that I don't know. So I'm gonna put T cable here, and this thing I'm gonna assume. So one assumption would be that all the tension, or the load in each one of those cables is the same one. Okay, so I'm gonna say, so for example, this cable A, and this B, and this is the one that you don't see, but it's called C, and maybe this one is D. Well, so TA equals to TB equals to TC equals to TD, and maybe just for the sake of it, just, tension of the cable. Okay, so they are telling me something else, 30 degrees from the horizontal. So maybe you can see that the top of the box is the horizontal plane, so I can see something like that. This one would be my 30 degrees. Okay, so that's kind of the idea. Maybe I can do this in a better way. This is my cable. Okay, so I have this thing. It's the point where the rope it's pulling up with 300 pounds, so that I can lift the box. Here I have my 30 degrees, and I have this tension. It doesn't really matter if I put this arrow going down or up, okay, because cables can only be in tension. Okay, maybe there are some other elements, structural elements like trusses, okay, that can be in tension or in compression, but cables can only be in tension. So whether you are taking this point of view, this is the point of view of this hinge or the hook that is putting together the rope and the cable. Okay, so in that case, this one is the tension of the cable. Okay, so I'm gonna do this, and let me just do, this is direction Z. So let me just put as, maybe this is Y and this one is X, or whatever you want to call it, but just in C. So at C, I have 300 pounds going up. Okay, so these guys are going up, and all of the cables are going down. So I'm gonna put minus 4 cables multiply by the tension of each one of those, which I'm gonna call just cable, and the part that it's going down, okay, is sine of 30 degrees. Sine of 30 degrees. Okay, that's the part that is actually going down in Z direction. Okay, this is not the one that I'm looking for. Okay, so this one should be equal to 0. My only unknown is I'm sorry, because I I'm saying almost temperature because I always look at capital T as temperature, so tension of the cable. In this case, if you calculate this, the tension of the cable is going to be around, if I didn't make any mistake, this one is going to be equal to 150 pounds. So each cable is trying to lift it has a load, okay, in tension of 150 pounds. That's kind of the idea. Now, let's just work out the normal stress for each cable. So I'm going to pick this. This is force divided by area. That is T of the cable, okay, divided by the area. Okay, so the area is the cross-section area of each cable. So the only thing that they are saying is that, well, you know what? The diameter of each cable is 1/4 of an inch. So that means that I have the I and then 0.25, and this guy is squared because that's the inches, divided by 4 because it's diameter instead of radius. So if I do that, well, you can also put all these things here, and you can say, well, 0.25 squared, okay, and then multiply by 4, which is this 4 that instead of looking here below, I can put it over in the numerator. Okay, so long story short, you have everything you need here, and this will be around, I think I have it here, and it's around 3.055 KSI. Okay, this means 1,000. This is 1,000 pounds per inch squared. That's what it means. Okay, so maybe you can see that you have your 150 there, you have your 4 here, it's around 600, and this small number, but this is around 3,055 pounds per inch. So in that case, this means that it's 3.055 thousandths of pounds. Okay, that's the basic idea. Now, let's just calculate a safety factor. So the safety factor is, well, there are many definitions, but all of them are really related. In this case, it's the maximum stress divided by the working stress, or the current stress, or the actual stress, whatever you want to call it. But this one most of the time depends on the material, and this one depends on the situation. Okay, so having said that, I'm gonna just say, well, okay, so the ultimate one is 60 KSI. Meanwhile, the working stress is 3.055, which is gonna give me a really large safety factor, which in this case is 19.63. Okay, this has no units, so it's around 20. You can say that the safety factor is around 20. Most of the times you will see that it can range, but most of the times you have safety factors, I don't know, from let's say 1.5 to 5 or something. The bigger the safety factor, the better. And there are industries that you need to have a really big safety factor, for example, in aeronautics, in airplanes, aircrafts design, and that type of things. Those things needs to be really, really safe, because one mistake is not like you have a car mistake. You have a car mistake and maybe the tire, have a problem or something like that. Well, not big of deal. Those type of things can fail. Sometimes they fail, and sometimes they fail badly. But in a case of in a plane, for example, nothing should fail. Okay, that's kind of the idea. Aerospace, that type of things should be always have a high safety factor. However, this 20 as a safety factor is too much. So hopefully I have done this thing with the right numbers, okay? But that's the basic idea behind this problem, okay? One more thing that they are asking is that, see, what would it mean if the safety factor was found to be less than unity? If that happens, so you can say, see, failure can occur. So failure or will occur. Let's just open the possibility. So failure can occur, that is, you are working above the maximum stress. That is what having a safety factor below 1 means, that your working stress is higher than the maximum stress, so you are set to failure. That is what safety factor below 1 should mean. That's it, guys. Let's just see you in another video. Okay, so let's go, guys.